It's a pleasure to have another talk in the Every Proof Assistant series. Today, Jamie Vicary is going to talk about a wonderful proof assistant where you don't even type anything. You just move your mouse. You are going to see it's quite nice. The slides have just been posted on the chat if you'd like to look at the slides separately. Jamie is okay. So here's a small puzzle for everyone. Why is he wearing a jacket and where is he recording from? But other than that, let me shut up and let's have Jamie speak. Jamie.
Thanks, Andre and Anya. Thank you so much for organizing this lovely seminar series. And hello, everybody in the audience. Those of you I know, those of you who I don't. It's great to get to know you and your group, and maybe the other people who are here. I have a small baby, so I'm working in my garage so that I don't have to hear the noise, and I can just pretend I'm like a bachelor living alone in a horrible garage. So that's why I have my coat on. It's bloody freezing today, even though I've got my heater. And I have this blue background because it's so embarrassing, all the crap I have in my garage. Okay, so the other thing I wanted to say is please feel free to ask questions. There aren't any stupid questions. What we're doing is quite unusual in this project. And if nobody asks questions, I get the feeling that I'm just a mad person in his garage talking about some crazy stuff. So please ask questions. I mean out loud, because I'm not really looking at the chat and all of that stuff. Okay, so today I'm going to tell you about this proof assistant called homotopy.io. We'll have some live sessions. You can go. This is the URL homotopy.io, and you could go to that in another window if you want to have a look already. And this is a proof assistant for geometrical higher category theory. There's an archive link there. Oh, and I've been practicing this. Thank you very much for welcoming me to your seminar za temelie matematike in teoretyczno rachunalnictwo, also known as Every Proof Assistant. Apparently that's Slovenian for Every Proof Assistant. Okay. So higher category theory is important, as we know, in many areas of mathematics and computer science. In computer science, we often focus on the relationship between higher category theory and the structure of groupoids, right, and type theory. But high category theory is used in many other areas. Quantum field theory, representation theory. People are starting to apply it in all sorts of areas. And in all those areas, the practitioners face similar problems, I would say. How can we formally define the structure that we're working with? This could be some proof, some high dimensional proof. Could be a manifold, a two group, some sort of higher algebraic structure. Could be geometrical, could be a knot. Having defined it, how can we, it's no good if we've defined it in some abstract way that nobody can really perceive or understand. How can we communicate this structure we've encoded to our collaborators, our readers, maybe people who aren't as expert in this subject, of course, communicate it to ourselves as well. And can this representation be dynamical? So can we modify a representation, discover its properties, prove theorems about it, right? Rather than being a static entity that we construct and merely observe. And of course, how can we use computers to help us achieve these goals? Not only in theory, right? It's nice to say, hey, everybody, look at my proof assistant. In principle, I could prove all this stuff. But it's even nicer if actually also in practice you can prove all this stuff, right? Because we have some very sophisticated systems where we know we could prove something's a principle, but in practice the proofs are too hard to construct. So these are familiar goals to anybody who's done serious work on any area related to high dimensional type theory, high category theory. And in my view, and I'm sure the view of many people here, this is the mathematics of the 21st century. And even though we've made a lot of progress in different areas, I think it's surely the case that we're really only starting to glimpse what is possible. And it feels to me that we're at a very early stage as a broad community thinking about these ideas. I think in 100 years, there's going to be some very beautiful, powerful things that are understood. And we will be able to look back from that point and see the naivety in the sorts of things we're doing now. So I think it's good to approach these sort of areas with an open mind, thinking, what are we missing? What else could we be doing? So I'm going to talk a bit about the graphical calculus, which some people might not have thought too much about before. It's conjecture that n categories have an n-dimensional graphical calculus, which is some sort of geometrical entity, like a picture. So here's a two-dimensional picture. And the motivation, or one conceptual motivation for these, is that they should be the dual of the ordinary pasting diagrams, commutative diagrams we're familiar with from category theory. So here's a pasting diagram. Maybe it involves 6 categories, A, B, C, D, E, F. Maybe it involves 7 functors, which are these single-barreled arrows, and maybe 2 natural transformations, S and T. We've pasted them together. In the pasting diagram, the categories A, B, C, D, E, F represent points. In the dual diagram, A, B, C, D, E, F represent regions. In the pasting diagram, S and T fill the entire two-dimensional space. In the dual graphical calculus representation, S and T represent points. So as we translate between these notations, an n-dimensional entity becomes a 2 minus n-dimensional entity in the other representation. So in one sense, these are formally dual to each other. So you might say, well, what's the point? If they're dual, then each is as good as the other. But in fact, that's not the case. There are certain things that are easier, much easier to handle from one perspective than from the other. So the idea of this graphical calculus goes back to Roger Penrose, physicist and mathematician, who's just won the Nobel Prize, of course, in 1971, who said, you know, he was working with general relativity, he had all these tensors that he was composing, and he said, it's really irritating using index notation to describe composite tensors. Why don't we just draw pictures where tensors are vertices and wires show us the indices that we're contracting? These pictures somehow have strict associativity and unitality built in. So we can make the convention when we draw these pictures that we simply don't denote any associators or any units. So if we compose with a unit morphism, we just don't depict that, and that somehow doesn't corrupt the notation. And that's one of the simplifying aspects. Joyal and Street, of course, developed the graphical calculus from monoidal categories on a formal basis in 1991. We've now got a nice treatment, much more recently, by Barrett, Moisberger, and Schaumann in 2012 for gray categories. In high dimensions, no formal theory has been developed, so you can't really read anywhere what is a 7-dimensional graphical calculus diagram, what rules does it have to obey, what are the isotopy laws, so on. Nonetheless, even in high dimensions, graphical calculus is regularly used as an informal language. One of my favorite examples, oh, I've taken it out, oh dear. I had a nice example, but that hasn't survived the editing area of my slides, so let's just move on. So in the graphical calculus, the point is that we can compose cells of our n category by drawing these composite diagrams. And then we say that any 2 composites are equivalent in the n category just when the 2 diagrams are homotopic to each other, something we'll see a lot throughout this talk. So the graphical calculus suggests homotopy as a basic mechanism with which to give our theory of high categories its dynamics, right? How do we manipulate terms, execute computations, and so on? Now, in the strictest definitions of high category theory, strict n categories, strict infinity categories, we don't allow these manipulations, but we know that these are insufficiently general, right? We know that not every weak n category is weakly equivalent to a strict n category. So clearly, we want to have some language that's more expressive than the theory of strict n categories. So we could look at the theory of weak n categories. In the theory of weak n categories, we have fully general, right? There's nothing that can be expressed in the theory of n categories which we don't have available, but the language can become extremely bureaucratic. So there can be things that we want to prove, which can be relatively straightforward to prove conceptually, but then when we actually try to express the proof in the language of a weak n category, we can very quickly become bogged down because of the level of bureaucracy and the fine details which the theory wants us to supply. So people often think about if there are other interesting points at which we could choose to live. So we could imagine weakness and strictness living on a spectrum. Of course, it's not the case that there's a total order of such things, but we can use this as a device for now. So it's often said that a model of high category theory is semi-strict if it's somehow as strict as possible while still allowing arbitrary homotopy theory, right? So that is still with the property that every weak n category is weakly equivalent to a semi-strict n category. And the theory of gray categories is one such answer in dimension 3. And semi-strict n categories are often held up as somehow the nirvana of simplicity for high category theory. Now, if you've got an n category, you want to prove that it is an n category, then you want a definition of n category with as few axioms as possible. And a semi-strict definition of n categories will do that for you, be useful for that purpose. But much more often, we're concerned not with proving that a certain structure is an n category, but we're concerned with building proofs in that n category. And then in that case, semi-strictness has the following problem. It's a bit like, you go to a foreign country and you say, okay, I don't speak the language, I want to be able to communicate. So you buy a guidebook. Now, you look at all the guidebooks, some are very fat, some are very thin, and you think, well, I want the smallest possible guidebook, which somehow guarantees to give me a fully expressive set of phrases. So you might find a very short guidebook, you might memorize, the few phrases that are in there and persuade yourself that, yes, anything that I could possibly want to do in this foreign country, I could do by some combination of phrases from this guidebook. And that could be true, but nonetheless, you could find that some things are extremely difficult to express with the limited phrases you have available. Things which would be much easier to explain if you had a more powerful command and a richer language available, right? So the problem with that, it's an analogy that's supposed to illustrate the idea that a semi-strict notion of n-category theory can actually be far from ideal for the purpose of building proofs, because the homotopy generators, the generators for higher structure that you have available are so few, even though they are in principle fully expressive and later span the entire homotopy space up to equivalence, you might have to build some extremely long composites to do that in some places, where a weaker theory, you might be able to do it directly, say in one step. So in this project, we have this notion that in fact it's better to be semi-weak. It's better to be as weak as possible. That is, give yourself as much expressivity in the language as you can, while being strictly associative and unital. So the idea there is that associativity and unitality, if you are strictly associative and unital, then in some sense composites are unique. So if you've got some stuff that you want to compose, strict associativity and unitality says there's basically just one way to do that. But then other than that, you have as much weakness as possible, and that gives you expressivity to then manipulate those composites.
Can I ask something here?
Yeah, please do. Hi.
So about when you talk about associativity here, do you talk about just the first level of associativity or also about higher associator?
So I would talk about associativity of composites of n morphisms, composites of cells in any direction, and also the higher structure that arises from that, associators, pentagonators, and so on. Right?
Okay, thank you.
But I'm not referring there to the sort of third area of weakness in a higher category, which is the interchanges. So we'll see more about that later.
Can I ask another question?
Yeah, great, Andrew.
So should I think of composites being unique as saying we have chosen composites, or they are unique up to something, or they really are completely strict, or
you should think of it as the following. So by the way, it took me, I was thinking about higher category theory in my research for a long time before somebody told me, in fact, I think it was probably John Bayers, that all that higher category theory is a language for composing stuff in n dimensions, and then expressing the fact that some composites are isotopic to other composites. That's it. That's what the entire language is. So when I say unique composites, what I mean is the following. If you've got a bunch of things in n dimensions, a bunch of n cells you want to compose in n dimensions, suppose you understand the way in which you want them to be composed. You want this bit to be over here, you want this bit to be over here, you want this bit to be over here. There are nonetheless a variety of ways you could do it. So imagine you have 3 pebbles, and you want to arrange these 3 pebbles in a line on your desk, right? You could put the first one down, then the second one, then the third one. Or you could put the third one down, then the second one, and the first one. Maybe you could put the first two down simultaneously and then put the third one down. There's many ways you could do it. But at the end of the day, all you see is 3 pebbles on your desk. Okay, you can't tell how you composed them. All you can see in the end is the result of the composite. Okay, and that's often desirable because all you wanted to do perhaps is form some particular composite. Of course, you had to compose it. You had to choose some way to form that composite as you built it dynamically, but you're not interested in remembering which one you chose, and you don't want that information to be recorded. So that's the idea. Okay, so there are many ways syntactically to form composites which are essentially identical, that is identical, that are equal up to associators and unitors. We want to have a representation in which the composites are literally the same term that you get out. So we've built a proof assistant for semi-weak higher category theory, so strictly associative and unital higher category theory based on an underlying theory which we call associative N categories. So this proof assistant lets you build terms in a finitely presented associative N category. So it's a bit like a CW complex or something. So you give your generators, and then this theory, this proof assistant allows you to compose those generators. And of course, you can add new generators and make your CW complex, if you like. Your computad would be another word for it. Your presentation as rich as you like. The proof assistant encodes internally these terms using a combinatorial notion that we call a zigzag, which is quite an elementary structure. We'll see how those work a bit later on. And the terms of this proof assistant, which are encoded by these zigzags, have an immediate geometrical representation, which the proof assistant shows you. So you're looking at a picture, and all interaction with the proof assistant is by direct manipulation. That is point and click. You don't type anything at any stage, you just use your mouse. So completely unlike, of course, most other, or certainly not every other, proof assistant for high category theory. There's a proof assistant, for example, constructed by Eric Finster to build composites in homotopic infinity categories, which has a similar point and click mechanism. Composition, of course, is strictly associative and unital in this theory. And all of the remaining weak structure is in homotopies of composites, so interchanges and higher dimensional analogs. So then we have this proof assistant, which can in principle encode, we would conjecture, arbitrarily complex homotopies, but that's no good if you can't construct those homotopies. So the system has high-level methods, which we'll see in action later, that let us say, for example, primarily take this large contractible region of our geometry and contract it. So it has a notion of contraction, which we'll see is very powerful. Now, this has been worked on, and this project, homotopy.io, and its immediately surrounding ideas, like associative N categories, been worked on by a wide range of people. It's my pleasure to call them out, particularly Christoph Dorn, who I worked with Chris Douglas to start thinking about associative N categories. Christoph Dorn has a very nice thesis on associative N categories. Other people have been involved in other aspects. Lukas Heidemann, Hu, David Reutter. Okay, so now I'm going to switch across to the proof assistant. So I'm going to stop my screen share just for a moment and then share my screen again. So share screen. Okay. So I hope that's worked okay, and you can see my screen. So you can follow along if you like. You fire up the Chrome browser. That's where compatibility is best, and visit the URL homotopy.io. However, I will be going quite quickly because I want to show off some different cool things. So you might find it a bit hard to keep up, but I encourage you to have a go. Okay, so in this proof assistant, what we have immediately is we have a finitely presented infinity category, and it is and we are faced with the empty presentation. So there are no 0 cells, no 1 cells, so on. So everything is correct as it should be, right? There's nothing to see, it's the empty presentation. So that all we can do initially is add a new 0 cell. So we click this button here, now we have a 0 cell. We can call it whatever we like. So I call it A. I could add further 0 cells. Maybe I could delete those. I think I'll stick with a single 0 cell. I'm now going to add so I can click on any cell here, and I can see a picture of it in the screen. Here it is. It's big, but it's still just a point. I can't do anything very interesting to it. Well, I could take its identity, in fact, by clicking this identity button. Now it's become one-dimensional. Now it's become two-dimensional, but I don't really want to do that yet. I'm going to clear that. What I want to do is add a 1 cell. So I want to add a one-dimensional generator. I need to specify its source and its target. That's the data I need to specify, just like in a CW complex. I'm going to give a new filler for some boundary. So I'm going to specify A as my source. So I click source. I click again, and I click target. So now I've got a 1 cell. We call it F. And this 1 cell goes from A on the left to A on the right. And if I hover over the middle, I can see this is F. So this is a 1 cell, and it's an endomorphism, so we can compose it with itself. We can do that by clicking on the right or on the left. And now here we see I've composed 4 copies of F in a row. And I did that by composing on the right, and then on the right, and then on the left. But we can't see any remnant of that. All we can see is 4 beads on a wire. I can't tell if I composed on the left, on the left, on the left, on the left, on the right, on the left, anything like that. So this is not a bracketed composite of F with itself. It's just F composed with itself 3 times, right? F composed with itself 4 times. Okay, so now let's build some 2 cells. So I've composed some things in dimension 1. That's nice, but there's not going to be any interesting homotopy theory yet in dimension 1. So now what can I build? Well, I could build an endomorphism of F. So I click F, I click source, I click F, I click target, and I've got an endomorphism. Maybe I could call this Q. Maybe we could have something like a monad object. So I get F, I compose it with itself, I click source, I click F, I click target. So here's something we could think of as a monad multiplication. Its source is F, and its target is F. And the thing itself I've called M. So, by the way, you might think, how's it drawing these pictures? Well, it's taking the thing that I specified as the source, right? The source of this thing M was a one-dimensional diagram. We see it along the bottom here. It's a line that was red, and then we had a yellow dot, and then a red line, then a yellow dot, and then a red line. The target of F, we see along the thing I specified, we see along the top, a red line, a yellow dot, and a red line. And then the way, that was all I supplied, the source and target of M. And the way it renders M is it draws the source along the bottom as a line, draws the target along the top as a line, and then it takes the cone on those, it contracts them into the center, and then there'll be a little singularity in the center, and then it patches that with a dot, called the dot M. And then it fills in the sides, and that's how it generates these pictures. That works in all dimensions. So let's make a few more generating 2 cells, maybe something that's like a unit for the monad. So it'll have F as the target and the identity on A as the source. We can call this guy U. Maybe one more thing, something that's like a co-unit. So F would be the source and the identity on A would be the target. I can call this C. So now we can start to compose these guys. Maybe I could start with M. I can click on the left and the right to whisker with a 1 cell. So the only 1 cell is F. So if I click on the left and right, it will compose with another wire. This represents the identity on F, I guess you could say. I could also click on the top and bottom to compose with some of my other generators. So if I click here, it says, it's not unique. What do you mean? Do you want to attach a Q here? So a Q is an endomorphism, you can see on the left of this wire. You want to attach a Q here and M here to these 2 wires, because M requires 2 wires coming in at the bottom right. A U or a C. I think I want to attach a U there. Down here, maybe I'll attach a unit on there. Maybe here I'll attach a co-unit. Maybe at the top I'll attach a multiplication. So now we formed a composite. This is a composite 2 cell in the finitely generated 2 category, if you like, on this signature. Now, we're in dimension 2, so not only can we do composites, But we also have homotopy. There's a non-trivial theory of homotopy in dimension 2. And the way that we execute homotopies in this system in dimension 2, as in every dimension, is by clicking and dragging entities in the graphical display. So perhaps I want an interchanger that takes this white dot and moves it up here left. I click and drag up and left, and it will be moved up. Suppose I try to move it up again. Now it goes even higher. Suppose I try to move it up again. The system complains, right, with something of a rather technical sounding error. The system knows that this white dot cannot move any further up because it knows it's blocked by these parts of the composite here, right? That makes sense. Suppose I take this white dot, this yellow dot here, and I move it maybe left. I get a complaint. I can't move that way. I can't move that way. That makes sense. We would expect to be able to do that in a 2 category, but I can move it down. That's great. Can I move this guy down? No. It knows I can't move it down because otherwise this green dot would crash into this green dot. Doesn't make any geometrical sense. What can I do now? I could take this white dot. Maybe I changed my mind. I didn't want to move it up there. I wanted to take it down and up and up. Perhaps something like this. Okay, so now what we've done is we started with a 2-dimensional composite, and then we've performed a bunch of isotopies, and we've ended up with a final 2-dimensional composite, which should be equivalent to the 2-dimensional composite we started with. And that should be represented by a 3-cell. And indeed, that's what I've been building up. You see here it says dimension 3, because the system is really constructing not the 2-cell we're looking at, but the 3-cell representing the entire composite isotopy. You can use this slice control to go back and see where we started, and then we can see everything that we did, right? By stepping through, we can see all the stages that we took. Okay, so how can we examine this? How can we inspect this more usefully? This is a bit like a CT scan, right? If you go to the hospital, you have a CT scan, you're given thousands of pictures showing slices through your body. That's not the usual way we represent ourselves in 2-dimensional form. We take a photograph from the side, which doesn't give full information, but it's at least an entire summary of ourselves. So, but we neglect one dimension. And so we can do that in homotopy.io by requesting to project out one dimension. So I set project equal 1. And now we see the history of our proof that we just built in projected form. It's a single 2-dimensional image. And it looks a bit like a braid diagram because the things that used to be vertices are now wires. And so the thing we started with, our initial configuration is along the bottom. The second proof step is the next slice. The next proof step is the next slice, and so on. So as our vertices move up and down, in this perspective, we see these lines that move side to side. So these are the world lines of our original vertices, if that makes sense. But now what I can do is I can take this, this representation, and I can notice something. Do you remember that we started with that white vertex? We moved it up somewhere, and then we moved it down again, right? Maybe we were exploring the space of proofs or something. Clearly, ultimately, that was pointless. Instead of moving our white vertex up and then back down again, we could have just not moved it around at all. And we can see that here. We can see this white line moves to the right over the yellow line, and then to the left again over the yellow line. So what we want to build is a homotopy now of this 3D geometry that cancels out that error, if you like, if we didn't mean to do that. And we can do that again by clicking and dragging. So I click and drag this here, I can drag this here, I can drag this here. I'm trying to move irrelevant parts of the proof out of the way. I don't care what I was doing with that green guy. I'm going to move this down, I'm going to move this down, move this down, I'm going to move this down, I'm going to move this up. I'm going to take this and push it down. I'm going to take this and push this across. And now I've cancelled that out completely. Now we can go back into our unprojected view, and we can scan through, and we can see that indeed now that white node, we now have a proof where that white node never went up here and back down again. We've modified, so we've constructed a 3-dimensional proof, we viewed it in projection, and we've simplified our proof in that projection. Okay, but in fact, when I was modifying that 3D proof, right, and I can continue to modify that 3D proof, in fact, what I was doing was building up a 4D proof, tracking all the ways I was simplifying that proof. we can view that in projection. We see this. Now I can take that 4D proof and I can simplify that 4-dimensional proof. But in so doing, I'm in fact building a 5-dimensional proof. And I can view that in projection. And I can think that 5-dimensional proof itself was more complicated than it needed to be, or perhaps I want to manipulate it, right? And so I can manipulate it as follows. So you can see in a very easy way, we can build up really very high-dimensional, sophisticated composites. Of course, we're not really achieving anything very spectacular here. We're just building random homotopies. But you see how easy it is to build up really quite rich, high-dimensional composites and structures. Okay, so now let's do something that people might recognize. Okay.
Can I ask a question?
Yeah, great, of course.
So you were projecting something out so naively without really knowing what it is that you were projecting. Does that mean that your higher dimensional manipulation was actually trivial in one of the dimensions because it was projected out?
That's right, that's right. So the system is, of course, storing information about all those dimensions that are projected out. It's not showing them to us. So the manipulations we were performing, we're only performing them in the 2 dimensions that we can still see. So you're right, there are some manipulations that we might want to perform, but which are hard to perform because they're somehow contained in those hidden dimensions that we've configured the proof of system not to show us. But we can, if we like, see the whole thing. So we can say, I've changed my mind, don't project out any dimensions at all. That's interesting. We've hit a bug there. It's disappointing. For some reason it's not letting me change the projection control. And then what we could see if we wanted to is we could see the entire 6-dimensional proof as slices of slices of slices of slices of slices of 2-dimensional things. So we could really see the whole 6-dimensional CAT scan of the proof if we really wanted to, and dive into any sub-slice of our proof. And in principle, we conjecture, although we haven't proved it, execute any homotopy in 6 dimensions that we like. And of course, that can sometimes get complicated to perform. That's true.
So the way you see the high-dimensional stuff is through the slices of slices thing, and then the user will move back and forth to explore what's going on?
Right. That's right.
Does your experience with the system, does it show that you develop a kind of a geometric intuition by looking at these slices?
I would say so. We'll see some examples, right? I'm going to prove a few non-trivial theorems now.
Okay. So the speed with which you can do it will tell us how much you internalize this stuff, right?
I think that's fair. And of course, it's all relative. There are still some things in this system that are too laborious to be practical to construct, and there are some things that are straightforward. Yeah.
Okay, thank you.
Okay, so the thing I'm going to construct now is the third Reidemeister move. So this is basically one of the axioms of a braided monoidal category. It's also one of the axioms of a gray category, of a tri-category, if you like. So the system somehow already knows about it, because it should know about homotopy theory in all dimensions. So I'm going to work in a braided monoidal category for this. We use the periodic table to realize that a braided monoidal category is a 3-category with 1 0 cell and 1 1 cell. So here's the 0 cell. I don't want to add, now because I've got this 0 cell here, let's call it A, I also have a 1 cell, the identity on A. So I've already got 1 0 cell and 1 1 cell. So I'd better not construct any more 0 cells, and I'd better not construct any more 1 cells. But I can construct some more 2 cells. So in particular, I can construct a 2 cell whose source is the identity on A. So I click A, I click identity, I click source. I click A, I click identity, I click target. Now we've got this guy. He looks like a dot. Might seem like a funny thing. It looks like a, let me call it maybe A. Oh no, that's a bad idea. X. It looks like a dot because it's got no y's in and no y's out, right? Because input was an identity and its output was an identity. I'm going to construct a couple more such guys. Identity source, A, identity target. We call it Y. And I'm going to do one more. I'm using the keyboard shortcuts for speed. There are keyboard shortcuts for all these controls in the top right, given by the underlined letter. So now I'm going to take these guys, and I'm going to compose them one after the other. So this is a two-dimensional diagram. We can check it's really a two-cell. So if we think about the periodic table and how we're using a three-category to represent a braided monoidal category, this should be an object of our braided monoidal category. And we can imagine it to be the object X, tensor Y, tensor Z in our braided monoidal category. So now I'm going to take the identity on that object, and I'm going to project out a dimension. So now we see three Y's. This is the identity. So now this is like the identity on X, tensor the identity on Y, tensor the identity on Z in our braided monoidal category. So now I'm going to perform some braidings. And I want these braidings to attach onto the side of this composite. So I'm going to do my manipulations near the boundary. That's a signal to the proof assistant to compose onto the edge of what the term I've already constructed. So in particular, I'm going to drag this to the right. So now it's moved that yellow object, so it's like in front of and indeed obscuring the purple object. And now I'm going to move it further so it comes across. So I've basically succeeded in braiding the yellow object over the purple object, but I've sort of done it very slowly. I don't want to do a half braiding and then another half braiding. I just want to do a single braiding more rapidly. So I'm going to click here and drag down, and that compresses the whole move into something we recognize as more like a braid. I'm going to do yellow-green braiding and a purple-green braiding. So what have we got here? We've got a yellow wire, a purple wire, and a green wire, and we're braiding yellow with purple, yellow with green, purple with green. Now the third Reidemeister move, or alternatively the naturality law for the braiding, says I should be able to take this braiding and drag it across here. And at the end, after rearranging it in that way, instead of braiding the first two wires, and then the second two wires, and the first two wires, in fact, I'll be braiding the second two wires, then the first two, then the second two. So the third Reidemeister move says these two different ways to braid three wires are isotopic to each other, right? Or if you like, the naturality law for the braiding in this case. So we're going to build that as a four-cell, right? One of these diagrams is three-dimensional in essence. It's a morphism in a braided monoidal category, so it's a three-cell in our higher categorical setup. So we're going to build it as a four-cell. So I'm going to take the identity on this three-cell to start with. Now, the proof technique that we're going to use is the following. We're going to insert at the bottom of our composite the final braiding form that we want and its inverse, and then we're going to cancel all the remaining junk and get rid of it. So what I'm going to do down here is I'm going to build what I want. So remember what I wanted to do ultimately, for the right-hand side of the third Reidemeister move. I want to braid the second with the third, the first with the second, and the second with the third. So we've got down here the right-hand side of the third Reidemeister move. What we're left with is all this junk up here. Now, if you look at this braid in everything above this line where my cursor is, you can see it's homotopic to the identity. Because this yellow wire is really doing nothing. If you look, it's completely on top. This green wire is completely behind, and this purple wire is in between. So this whole braid above where my cursor is isotopic to the identity. I now want to build that isotopy. So I'm going to use this really the only tool that this system has to build on trivial isotopes, which is contraction. Really, this whole upper 2/3 of the composite is contractible, and I want to contract it. But I can only contract pieces pairwise. So I could start here, for example. I could try and pull this down, but I get a complaint. And this surprised us a lot when we first did this. It took us a while to understand what was going on. It turns out something that the proof assistant's being very clever. It's complaining, it's saying this is not contractible. So what the hell's going on? Why doesn't it realize that this can be contracted? Well, when I click and drag like this, what I'm telling it to do is contract locally. So let's look locally at the braid in this area where my mouse is indicating. Purple is above green, and yellow is above green, but we don't have any information locally about whether purple should be above yellow or yellow should be above purple. So as far as the proof assistant is concerned, it's unable to contract this geometrically, because in so doing, it would basically be making purple, green, and yellow exist simultaneously. Everything, as we're looking at it, would be contracted to a point, but it has no idea of the intended relationship between purple and yellow. We can see elsewhere, we look here, that yellow should be above purple, but if we just try and contract this upper region of the diagram, the proof assistant has no idea. But there are other places in this top 2/3 where the situation is different. If we look here, we see that here yellow is above purple, and here purple is above green. So by transitivity, it's obvious that yellow should be above green. So in this region of the diagram, there should be enough information to contract. So I'm going to click this crossing and drag it down, and indeed the proof assistant has succeeded in contracting. And now this node, this point here, contains full layering information, right? It knows what should be above what. So I can now contract this up and down, and I can somehow hoover up that part, which has now got full contraction information, and I've managed to contract that entire part of the diagram. So I've contracted it sort of to a point. There's a single locus here of the homotopy, but I want the identity. I don't want this weird thing where they come into a point and go out. So I want to, the idea is always that you use your mouse, that the mouse move should be intuitive. So what I do here, so this yellow Y, you see, is coming in and is momentarily, tangentially, almost braiding over those purple and green wires, but then it decides not to. So I want to grab this point of the yellow wire, drag it to the right. Similarly here, I want to get this part of the purple wire and drag it to the right. And now we've finished our simplification, and we have the thing that we wanted, which is the right-hand side of this third Reidemeister move, braiding the second and third wires, first and second, now first and second. Now, we're recording everything that we've done.
Question?
Right? So, yeah, please, go ahead.
Can you drag something that's underneath?
You can. It's harder. You have to unproject, because you can't see it, right? So you would have to unproject and then go and look through the slices of your braid.
To find it.
Exactly. So here you see purple is in front of yellow, but because we're in the slice, we can see the green hiding there. Because in the projection, we're looking from the left, in some sense. Does that make sense? So you can do all of those things, but it can start to get a bit complicated. You have to keep your wits about you. Now, let's look at our entire proof in projection. Here it is. Here's our entire proof of the third Reidemeister move that we constructed. So you see, this system does know about the third Reidemeister move. As I've claimed, I claim it knows about all homotopy in any dimension, although we haven't proved that. But this proof looks complicated. Can't we give a simpler proof? Can't we contract our proof, as it were? And of course, yes, we can. We can contract it however we like, because it turns out this entire space in which we built this proof is contractible. So I'm contracting my proof, I'm contracting my proof. Wouldn't it be great to do this in homotopy type theory, by the way? You build some big proof and you think in the end, well, I enjoyed that, but I'm sure, there's probably some more compact way to do this, and tell the proof assistant, contract my proof for me, please. Right? But that's the sort of technique that's not available in homotopy type theory to my knowledge, but we do have it, of course, for this very system with very different sort of logical expressivity. So I can finish doing my contraction, and it turns out I can contract the entire proof to a single point. So let's see how this proof goes now. We start with the left-hand side of the third Reidemeister move. We pass through some singular point where this triple braid is happening simultaneously, and we end up here. So that's nice, but something else we can do with this system is we can render not only in 2 dimensions, but in 3 dimensions. So we can now render our proof of the third Reidemeister move as a single 3-dimensional image. And it looks like this. So let's try to understand what the system is rendering for us here. So let's look at it from this angle first. So we started off with X, Y, and Z being points. As we were building up our proofs, X, Y, and Z were lines, but in this representation, of course, X, Y, Z are surfaces. We can keep track because of the color scheme. So let's see on the left-hand side. So let's imagine this entire front face now. Let's understand this entire front face of the diagram. Here we braid the first and second wires. In this front face, of course, we have a green wire and a purple wire and a yellow wire. So here we see green and purple exchanging, green and yellow exchanging, and then green and purple exchanging. And on the other face, we see they're exchanging in the opposite order. And this 3D geometry is a representation of the way that what the third Reidemeister move does, which is basically passes these surfaces through each other. Okay. Next example. There's a couple more examples that I want to do. Then we'll do a little bit more theory.
I have a question.
Yes, please.
You've made a proof. Can you export a proof term in some type theory so that it can be verified independently?
No, we can't do that. It's something we would really love to be able to do, and I'll talk at the end. I very much want at the end of my talk to talk about things that touch on the relationship between our work and other things that have been done, say in Martin Love's type theory. And I'll talk about that later, Daniel. Is that all right? But no, we can't do that at the moment. It's a fantastic question, and it would be a very exciting thing to be able to do. Okay.
Can I have another question before you go on?
Yeah, please.
When you mentioned that your system sort of just sees how these lines are locally one on top of the other. So how far is this locally?
So the way that, so the only really high level technique that this system has is called contraction. And this contraction is binary. So at the moment, all we can do is contract some entity with some adjacent entity. There's no reason for that limitation fundamentally. Mathematically, we could, I guess, tell the proof assistant to contract any finite region. Maybe we could imagine like a lasso tool where we could select some region of the term and say, please try and contract this region. And it would either tell us, sorry, it's not contractible, or it would perform the contraction. But we just didn't. I mean, it's just a question of the UI. So at the moment, we can only contract adjacent pieces, but in principle, you could ask it to contract any connected, any ball, basically.
Mm-hmm. Okay, yeah, thanks. That answers my question.
Okay, so I'm going to do a couple more examples now of a slightly different flavor. The next example I'm going to do is the Ekman-Hilton homotopy, right? Of course, everybody here, I'm sure, knows that very well. It's one of the fundamental non-trivial phenomena of homotopy theory. It's something that's handled, for example, in the homotopy type theory book, and it manifests in many other algebraic systems. So let's see how we build that. We need to have, we work in a signature, in a presentation, as it were, with a single zero cell. And the entities, we can call them S and T, which are going to be involved, are both endomorphisms of the identity of A. So we can do that in our system, as we've seen. We click A, we click identity, we click source. We click A, we click identity, we click target. So here's this guy, we call him S. So his source is the identity on A, and his target is the identity on A. We'll do the same again. Identity source, A, identity target. So now we've built this guy T. So now we've got a presentation. We could build this presentation easily as like a higher inductive type or something. We could build this signature in many type theoretic approaches. We've got a single zero cell, and then we've got a two cell S, the identity on A, the identity on A, and a two cell T from the identity on A. Okay, so now what is the Ekman-Hilton phenomenon? It's a three cell, and it's a three cell that says if we compose S with T like this, that should be isomorphic to, equivalent to, equal to, whatever you want, however you want to express it, to T composed with S. So the composite in the other dimension. So how do we build that? Well, let's take the identity. So when I take the identity, that just means I want to compose the ways I manipulate this diagram. I want to store them all and compose them all together. In this case now to get a three cell. So I'm going to take this yellow dot and move it up. And I'm going to take this yellow dot and move it up again. Now I've finished. I've proven the Ekman-Hilton phenomenon. I built it as a three cell. Let's project out one dimension. Of course, it just looks like a braid. when we look at it like this, we see it's done this silly thing that this system always does, which still annoys me, that it by default does half braids. So I'm going to perform an isotopy of my 3-cell to yield a new 3-cell where the isotopy just takes place more rapidly. Now we could view this in 3D. Of course, what we see is 2 wires braiding in front of each other in 3D space. What else would we imagine? Right? We can. Oops, can I spin it around the other way? I can't for some reason. Okay, so that's the Ekman-Hilton argument in as a 3-cell in homotopy IO. Okay, so now we're going to do something even more complicated. We're going to construct the syllepsis. The syllepsis is the big sister of the Ekman-Hilton. The syllepsis says the following. If we have, so suppose that this Ekman-Hilton move, we call this gamma s comma t. The syllepsis says that if we take gamma s comma t and we compose that with gamma t comma s, this composite should be isomorphic to the identity on s composed t. So it's like saying the double braid is isomorphic to the identity on s composed t, but under a different signature, a signature where the source of s is not, where the sources and targets of s and t are not the identity on a, but the identity on the identity of a. So it's a phenomenon that exists one higher level of suspension. So the Ekman-Hilton argument is something that's been formalized in using Martin-Löf path types, right? It's been formalized in different scenarios. The syllepsis is not something that, to my knowledge, has been formalized in any other system. I would be delighted to be proven wrong. So let's now do it in homotopy IO. So we have a single 0 cell. We take the identity on the identity, use that as the source. The identity on the identity, use that as the target. So it's now appearing as a 3-cell. We call it S. And we do it again. We take the identity on the identity, use this as the source. Again, the identity on the identity, we use this as the target. We call this T. Right? In my previous tab, S and T were 2 cells. But here, when we're trying to prove the syllepsis, construct the syllepsis, S and T are 3 cells. So now I'm going to have to project out a dimension now to view S as a dot. Now I'm going to compose with T. Okay, so now I'm going to build the double braid. So I'm going to braid S with T and then T with S. That's the left-hand side of the syllepsis. So I'm going to take the identity. I'm going to braid yellow up and to the right. Then I'm going to braid purple up and to the right. Whoops, I take the projection. So it's done it as these silly half braids. I'm going to contract that a little bit like that. So this is the left-hand side. This is the source of the syllepsis. The syllepsis is a 5-cell, if you think about it. Like it's an equation between 4 cells. This is the source of the syllepsis as a 5-cell. So now let's construct the syllepsis itself. So I'm going to take the identity, as I always do, because I want to compose up the isotopies that I'm doing. So now we've got an identity 5-cell, and we're going to continue with the proof. Intuitively, what we want to do is use the extra dimension to take this first braid and change its sense. So instead of being a braid of purple over yellow, we want to turn it into being a braid of yellow over purple. So we do this as follows. We're going to use this slice command. Andre asked before about how we can see subparts of the proof that are hidden because of our projection. We're going to dive into this very slice here. We're going to have a look at what's going on in this slice. So I'm going to project 1 level less, and I'm going to go into that slice. So what we see is the blue. Remember, we're looking from the left, as it were. Is that right? Yeah, so you see purple is in front. So when we go into this slice, we're looking from the left, as it were, right? So we see that purple is in front. But we say, no, we don't want purple to be in front. We actually wanted yellow to be in front. And if you think about the geometry, you think about the additional degree of freedom we've got available, what we want to do is we want to take yellow and move it over the top of purple. So I take this S and I drag it to the left. S is now on top of purple. So let's project again and see what's happening. So what's happening now is that in the fourth dimension, if we neglect the fourth dimension, S and T are not braiding, they're actually intersecting. So the proof assistant's not able to render that as a braid. It really thinks they're touching. Of course, because of the additional dimensions projected out, they're not really touching at all. Now let's go back in. Now let's finish. Let's move it all the way over. Now we see what we've achieved. Now it's just a braid and it's inverse braid. So I can contract, I can pop this off, and now we've got the identity. So now let's review our entire proof. We started with the double braid, gamma composed with gamma. We're now going through the process of modifying this lower braid. So now at this stage of the proof, we've changed the sense of the braid, and now we contract and we contract. And we expand, and now we've got the identity. Let's project yet another dimension to see that entire proof as a single picture. We did 4 things basically, so we can see it in 4 stages. What else can we do? Let's view this in 3D. Try and get a better sense of what we're doing. Okay, it's a bit hard to see what's going on there. So maybe let's project out one fewer. Okay, so we start with the double. We start with the double braid. We modify the double braid, so these guys are actually touching in this 3-dimensional representation. Of course, there's one dimension being projected out, you see, so they're not really touching. We go a little bit further now, and we've now changed the sense of the braid, so it's a braid and its inverse rather than a braid and another braid. And we now modify, we form an isotopy in 3 dimensions to pop them off each other. Now, as is often the case, the proof that we've built can be contracted. So I click and drag, click and drag, click and drag. Now we've got our entire proof as a much more rapid entity. In 3D, it looks sort of nice. In 3D, we can't tell that this is a braid and a braid, or a braid and an anti-braid, because that information's been projected out. All we can see is that on this side of the proof, S and T braided past each other twice, and on the final stage of the proof, they didn't. But that kind of looks nice as a surface. Or we can project out fewer dimensions, and we can see the proof as we see the most efficient version of this proof. Where we start with a braid composed with a braid, and now we contract things. So it looks like they're intersecting. Of course, they're not really intersecting because there's an additional dimension that's being projected out. And then finally, we get the result. Okay, so that's an illustration of constructing the syllepsis as a 5 cell in a finitely generated 5 category in this case. Okay, so it's now 3 o'clock. I've got a little bit more theory I wanted to mention. But if you want me to stop exactly on the hour, I could stop now.
We are usually a bit relaxed, but half an hour would be too much. But if you just go on for a few minutes, it's fine. Yeah,
it'll be a lot less than that. Okay, so let me talk a little bit about what's going on under the hood and what the combinatorial foundation is that this proof assistant is using for its encoding. Well, let's look at this string diagram here. This is a string diagram, 2-dimensional. So this could represent a composite in a bicategory. Example, finitely generated weak 2 category. So we've got 3.
You're not screen sharing, Jamie.
There's something going on with screen sharing, yeah.
Thank you. I forgot to reactivate my screen share. There you go. All right. So look at this guy. This is a string diagram in a bicategory. So we've got a finitely generated bicategory with 4 2-dimensional generators, 4 2-cell generators, alpha, beta, gamma, and delta. Gamma, they've got various different sources and targets as appropriate for this picture to make sense. And now we can imagine drawing some horizontal lines across this diagram. We're considering some sort of stratified space. We notice that some heights are particularly important because they contain vertices. There are 3 such heights that contain vertices, right? This height, and this height. And I draw a solid gray line at those heights. And at the intermediate heights, above and below those, I draw, those are like we call these non-singular heights or generic heights. Nothing's really happening of much interest at those heights. And then what we can do is we follow along one of these lines, one of these heights I've specified. We can see how many entities do we intersect. Well, here for this top line, we intersect 3 entities. We intersect a line, a line, and a line. At this single height, we intersect 4 entities, a line, a vertex, and a line. So we can count how many entities we intersect at each height. Now what we can imagine doing is taking this dotted line, any of these dotted lines, say this one, and imagining that it gradually tends upwards until finally it converges on this adjacent solid gray line. And as we do that, we notice that these entities on the dotted line will converge towards certain entities on the solid line, right? This guy will flow up to here, this guy will flow up to here, this guy will flow up to here, this guy will flow up to here. So here we see that, so indeed we realize is that the geometry determines a function from the entities on this line to the entities on this line. Furthermore, the entities are obviously totally ordered, and this function will preserve the order. So what we get is we get monotone functions in an alternating pattern from this totally ordered 4-element set to this 3-element set, from this 3-element set to this 3-element set, and so on. So it's a sort of a sequence of cospans of monotone functions. And it seems a reasonable proposal that, in fact, if I give you any alternating sequence of monotone functions between finite totally ordered sets, you could take that data and you could use it to draw a picture in this manner. So that's how we encode 2-dimensional diagrams, for example. So what's the theory there? So this is the most theoretical slide of the talk. For any category C, we define its category of zigzags, another category Z of C, as follows. An object is a sequence of cospans in C, where of course the adjacent cospans have to have matching objects. And then a morphism from a sequence of cospans X to a sequence of cospans X prime, so F going from a sequence of cospans X to a sequence of cospans X prime, is the following. It's a monotone function between the target objects of the cospans, built from morphisms of C. So I build the graph, as it were, of that monotone function, and I actually instantiate these guys as actual C morphisms. Then between the regular levels, which are the sources of the cospan morphisms, there's always a unique way to fill in with identities. What we're left with is now a bunch of squares. And we ask that these be commutative squares. And then we're done. So for any category C, we have its category of zigzag, Z of C. And I'm going to zoom on a little bit. We define an untyped N diagram to be an object of Z of Z of Z of dot 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 of Z of 1, the terminal category. So let's give a few examples before I finish. Here are 53 examples of 0 diagrams, all objects of the terminal category. Okay, nobody can...
Could we see the previous slide for a few more seconds?
Yes, of course, Daniel.
All right.
So for any category C, we get a new category where objects are cospans in the original category, basically, and morphisms are some sort of monotone function-like entity between them. So here are 53 examples of 0 diagrams, all objects of the terminal category, fair enough. Here are 7 examples of 1 diagrams, so all objects of Z of 1. So what is the zigzag category of the terminal category? Well, it's just the regular simplex, it's just the simplex category delta plus. So objects are, so plus here means that I also allow the empty set. So objects are finite, totally ordered sets, morphisms, and monotone functions. That's the category Z of 1. So these cospans are entirely determined by their length. Here we have a cospan, a series of cospans of like 3. There are 3 cospans here, there are 4 cospans here, and so on. So there's 7 such diagrams. Here is one example of a 2 diagram. That is an object of Z of 1. That is an object of Z of delta. And of course, it's the diagram that we started with, right? So it's a set of cospans of cospans of cospans of nothings. It's cospans of cospans of cospans of objects of the terminal category. And that's how we build up our geometries. And that's what the proof assistant is storing under the hood. It's storing cospans of cospans of cospans of cospans of nothing. Of course, we also need types. So we sprinkle labels. All these points come from some label set. And then we have some notion of type checking, where we can expect the neighborhoods of all of these points and verify that these neighborhoods are what we expect. And of course, I'm sweeping a huge amount under the hood here. You have to look at some of the papers that we've written. But we then propose that this type checking algorithm exactly passes as correctly type checking not only things like this, which this is a relatively trivial composite, there's no homotopies here, but also things like the syllepsis, right? The syllepsis is a valid 5-dimensional homotopy, and it passes our type checking algorithm. Okay, so just to finish, I want to conjecture about how these ideas could be related to other ways which, as computer scientists and mathematicians, we like to think about high-dimensional algebra. So as we're familiar with in Martin-Löf type theory, coherences for path types, which we might construct, say, using the J rule, J types, coherences for these path types must be inserted by hand where necessary. So if we have 3 paths, F, G, and H, which are all nose to tail composable, we could compose F with G and then with H, or we could compose F with G and then H. And these will give us 2 different composite one-dimensional paths. These composites will not be definitionally equal to each other in the type theory, but we could build a 2-cell going between that we call the associator. So we have to build these things by hand where necessary. So the one takeaway from the Homotopy.io project is that it is possible to build a useful system where some of this structure, including in particular associators, is trivialized. So, and this is all entirely future work, but I think it's exciting to talk about. Could we firstly imagine some sort of translation between these engines? So could we imagine taking the formalization, say, of the syllepsis, which I've just presented to you a few minutes ago, and extracting from it a correct term written in the language of J types in Martin-Löf type theory that represents the syllepsis. The J rule is weak in some sense, right? It has to have to explicit associate explicit unitors. So that extraction, that conversion procedure, would have to add a huge amount of structure. And I bet what we'd end up with is a proof which is in some sense large, right? I mean, if you serialize the Homotopy representation, you serialize the Martin-Löf type theoretic representation of that conjectured term representation, it would be much larger, I suggest. But what else could we imagine? Well, we could imagine using similar ideas, but somehow under the hood. So suppose I have a pair of function types which are not composable, but which are, say, composable up to associativity, right? Let's say F goes from A to B, and G goes from B prime to C. So B is not definitionally equal to B prime, so we can't compose F and G, say as paths or whatever. But maybe B and B prime are equivalent up to unitors or up to associators. Then couldn't we imagine a system which under the hood is able to trivialize or recognize as trivial some part of the path type and say, okay, up to this amount of trivialization that I'm able to perceive, we can treat B as in fact definitionally equivalent to B prime, and the system, the type theory, could then allow you to compose these functions. Or alternatively, instead of automatically trivializing some path type inhabitants, perhaps it could automatically insert them. So when you try and compose F and G, it would say, well, sorry, mate, F and G aren't composable, but I can automatically coerce G, so it doesn't have type B prime to C, it has type B to C. So it'll give you back some perhaps much larger thing, but now you can compose it with F. And I'm giving a hottest talk a week today where I talk about some type theoretical work that we've done. So there'll be no string diagrams in that talk next week. We talk about our ideas to do exactly this for some fragment of the type theory. Another thing to say is that our proof assistant homotopy IO lets us work with finitely presented infinity categories. So these are directed, by the way. Actually, it's quite hard to make them undirected. A project we have at hand at the moment is being able to mark certain of our generators as undirected, because it'd be nice to be able to work with infinity groupoids as well as infinity categories. But of course, homotopy IO doesn't let you take products of your one cells or sums or anything like that, right? It's not a logic in any sense, right? It purely lets you work with path types, but nothing else. But what if we could get the same sort of advantages as we have, these sort of semi-strictness advantages that we have here for paths? What if we could also get those for other aspects of a logical system, say like products or sums? And imagine we could even manipulate those geometrically in some sense, right? So I'm imagining, for example, the sum of a pair of diagrams could be their disjoint unions. You can imagine two diagrams floating in space. That seems perfectly reasonable. What about their product? Well, it could be the Cartesian product of the geometries. It wouldn't really be a geometry anymore in the same sense. It would be like a branched geometry type entity. Wouldn't be a string diagram as we traditionally conceive it, but it could still be some sort of geometrical object. And it could potentially be the case that we still have some semi-strictness there, and potentially that would be a setting where we could manipulate, where we could but effectively be working in, say, finitely presented n category with products and co-products in a way where we still reap some advantages of semi-strictness. That's the end of my talk. Thanks very much for listening.
Thank you. Questions?
I have a question.
Go ahead.
Can you start with an arbitrary simplicial set and use zigzags to make an infinity groupoid from it?
So if you had a CW complex is basically a sort of simplicial presentation, like a simplicial computad. So although our framework is not a framework for simplicial high categories, it's a framework for globular high categories, right? I mean, it's, in the traditional sense, you could probably imagine taking your CW complex and in some reasonable way turning it into a presentation. Is that what you're asking about? Maybe I haven't understood the question very well.
Well, no, think of a category. So in an arbitrary category, you could consider these zigzags, and you could try to make those zigzags into arrows inside some sort of infinity groupoid using the maps you defined in the higher cells and so on.
So certainly starting from any base category, if you consider, you start with any base category C, if you consider Z of C, Z of C, and so on, in some sense you can crush these all together and you can build something we call Z infinity of C. You can think of that as like the infinity category, like arising from zigzags in C, and that could perhaps be a way to do something along the lines of what you're asking. I may be not familiar enough with simplicial approaches to high category theory to give a very good answer to your question. Maybe you're not satisfied by that.
No, thank you. Thank you very much.
Yeah, I've got a question.
Hmm?
I've got a question.
Okay.
So maybe, well, so I very much like the tool, and maybe I haven't understood enough in this question that might show that, but I'm interested in your choice of where semi-strict lies and to what extent it's a sweet spot on that horizontal line you had earlier on in the lecture between weakness and strictness. So when I was seeing your examples, I mean, the kind of thoughts I had was, well, if one wants to reason in a braided monoidal category, one really wants the Reidemeister move to be an equality, not a higher cell. And on the other hand, if one wants a tool that is going to reason about examples of weak higher dimensional categories that one wants to deal with, then there are many such categories where the weakness specifically comes in because composition is not strictly associative. So somehow I'm not quite sure. So a sort of very weak end seems very natural, and also a stricter end of the line seems very natural, but I'm not quite sure why semi-strict is natural, and that was puzzling me through the talk. But then I guess at the end it's justified by your zigzag model, and that's the combinatorics you use to get the model to work. But is there something more deeply nice about it than that it works computationally?
So there are certainly other things one can imagine doing. So the reason you don't want to work, as you know, in a strict setting is that not every weak n category is equivalent to a strict n category. So if we build a proof of system that let us work with strict n categories, there would be some things we just couldn't express, right? Like the Ekman-Hilton phenomenon wouldn't really make any sense. But you're right, it would be nice, though, maybe to work in a braided monoidal category represented in a way such that the third Reidemeister move was a triviality. That might be nice. Now, the third Reidemeister move has to do with the interchange structure. So maybe not everyone's aware, but if you look at the definition of a strict n category, there are three classes of axioms: unitality axioms, associativity axioms, and interchange axioms. If we weaken all of those, we get three weak n categories. In this system here, we've only weakened the interchanger. We've kept the associativity and the unit laws strict. So these diagrams obey precisely the same strict unit axioms and strict associativity axioms as the definition of a strict n category, but they don't obey the strict interchange axioms. Now, we could say it would be nice maybe to work for braided categories, maybe other scenarios, in a representation where the third Reidemeister move is trivial. The third Reidemeister move comes from the interchangers, so maybe we could strictify the interchangers and maybe also strictify the associators. We can't also strictify the unitors because then it'd be fully strict. So if we leave the unitors weak, we strictify interchangers and associators, but just keep weak unitors. And in fact, that is something that you could potentially do. And it is conjectured that every weak n category is weakly equivalent to an n category with strict associators and strict interchangers, but not necessarily with strict unitors. These are called SNU categories, which I think is supposed to stand for strict no unit. And one could imagine building a tool to work with infinity SNU categories. And I can tell you very much, in fact, what that would look like. It would look like manipulating proof nets. Because in proof nets, we see graphs. We don't really care about how we embed graphs on the plane. So if we move some bit of the graph down or some bit of the graph up, we don't care. Part of our embedding, it's just a graph, it's not an embedded graph. But then we have to link different parts of our proof net with little unit wires, telling them how they're attached. So I believe very strongly that we could have a different sort of proof assistant for category theory, which involved manipulating like n-dimensional graphs, hypergraphs in some sense, connected by some unit wires. I mean, that would require a completely different combinatorial model. In fact, I've got a student working exactly on trying to do something like this. It looks very difficult. Not very difficult, but I mean, maybe just as difficult as this, but we've been trying to do this for 5 years, right? This has been a long program. So you could do that. It would be maybe better for some purposes, maybe harder for other purposes. What would be fantastic would be able to translate between all these perspectives. Imagine there's some homotopy, we're trying to build some complex inhabitant of some path type in homotopy type theory. Imagine we have a go, but maybe we get a bit stuck. Imagine we take our type theory, we export it into homotopy IO, we visualize it in this strictly unital, strictly associative representation. We maybe perform some homotopies, we get stuck. Maybe we extract it from that tool and now embed it into a different tool, which trivializes the interchanges and the associators, but keeps the units being weak. And now maybe from that representation, we see something else we can do. Then maybe we can embed it back into Martin-Loeb type theory. Should be entirely possible in principle and exciting and powerful. Goodness knows what you would be able to do with all of those techniques at your disposal. It should be possible in principle. I think that's very exciting.
Yeah, indeed. Can I just follow up with a specific question just related to that? So if you made all homotopy equivalences identities, is that as strict as a strict category? Does that?
That's right. That would be too strict. So there would be homotopy that can't be modeled up to equivalence.
Yeah. Okay. So the geometry is not sufficient, as it were, to give the level to dictate what the right level of strictness is.
Yeah. Fair enough. I can say something else interesting, but maybe there's another question. So maybe just quickly, the other interesting thing I wanted to say is that actually weak higher categories are much easier to implement. If you want to build some proof assistant to work with high category theory, it's much easier to build a proof assistant to work with weak high categories than for strict high categories. There aren't any proof assistants that let you work easily with strict high categories, and for good reason, because given any two composites, we don't know any algorithm to determine if these composites are equivalent under the axioms of a strict infinity category. It's extremely difficult problem. What we're basically saying is we've got two geometries in arbitrary dimension. Are they isotopic? Right? This is an extremely difficult problem, right? It's like saying, you know, in some monoid, or I've got some presentation, it's a vast generalization of the word problem in a monoid, right? This is very, very difficult. So it's actually weakness that's easy, because weakness is just the raw syntax. To get any strictness at all is a difficult thing, because you have to find some syntax that can carry that faithfully, right? The power of this tool is that there's no sense in which it's having to, in the hood, desperately try to find some sequence of associators that can show this term's equivalent to this term and check everything's taking place correctly under the hood. It's using a representation which is natively strictly associative and natively strictly unital.
I have a question that might be of interest regarding your findings in designing the interface, because I'm almost surprised that the picture you see on the IO side is so minimal still. For example, you only show one level at once, and you don't indicate, for example, the slices in the pictures. How did you end up like that? What was the process, or do you have other insights in designing this graphical interface?
Well, when we designed it, one design criterion was to keep it as simple as possible, right? Because the more crap you add to the UI, it can have even though you're trying to make it more powerful, easier to use, it can make it off-putting. Ultimately, this is a system that lets you input a signature and then build some composite in the free infinity category on that signature. So I only wanted you to be able to see two things, the signature and the composite, and that's it. Now, as we go into higher and higher dimensions, and as one gets more expert with the tool, absolutely, one very quickly runs into more complex requirements, right? I'm often thinking, oh, I wish I could simultaneously see all these slices. In fact, I've even got a grant with one of my current grants, a line item for a virtual reality headset. I imagine that you could be like, walk through these proofs. You know, I'm not going to do that. I'm going to need some summer student to do that. That's never quite happened. But the question of how you work with these in high dimensions has been a good one. But as I say, whereas it comes to our ethos for designing the UI, we just tried to keep it as simple as possible. And we only added UI components where they were, you know, critical, and added some, you know, gave some substantial quality of life improvement for the user.
I'll forward a quick question, or if I may.
Hmm?
So regarding connecting this up with the proof assistant, you could actually try to make it somebody else's problem, because internally you must have a data representation of your zigzags, and that's the meat of the thing, right?
Yeah.
So if you just dump the zigzags into a proof assistant as pure data, then it becomes somebody else's problem to figure out how they're going to convert that to a proof in whatever system they think they're in.
Come and get it, guys. It's all here. I'm happy to give you the zigzags in that full raw.
Right? I mean, in a formal sense, the zigzags are the formal proofs.
Yes, that's right. That's it. That's it. We then have of course, it's, we have a type checker of sorts, which can take one of these zigzags and tell you if it corresponds to a correct composite in some finitely presented infinity, or if it's just garbage, because you can build some garbage thing. So we have a type checker.
Okay, so there is some work there, because whatever your type checker is doing, the proof assistant will be doing as well.
That's right. For example, you could imagine we could have some F from A to B, a one cell, and some G from C to D as a one cell, and we could build a zigzag that composes F and G. That's of course garbage as a composite, but you could build it as a zigzag. But in our tool, we have a type checker, and anytime we do any manipulation, basically it does the manipulation at the level of the zigzags, and then it runs the result through the type checker. Sometimes it says, sorry, the result of what you tried to do was garbage, for example, and then it would throw it out. For example, if I tried to take F composed G, and I try to move the F through the G, so I get G composed F. That's just garbage if these are one-dimensional paths, and it would detect that. I mean, it would do it internally, and then just before it shows it to you, it would run it through the type checker. The type checker would say, sorry, this doesn't make any sense. And we claim that that this type checker does indeed correctly detect precisely those zigzags that represent genuine n-dimensional geometries in the manner of the theory of infinity categories. We don't have a proof of that. We don't have a proof that our theory corresponds exactly to some known model of infinity categories.
Okay, but you don't have to have a completeness. I mean, in order to make a useful tool, you just need to know that it's sound, in the sense that if you manage to do something, then you actually get a proof of something out.
That's right. So that's something so that's something that we've tried to do. We spent months trying to do that, my collaborators and I. And so we're currently trying to do something much simpler, which is still very difficult, which is just do this for the strictly unital theory. So we're saying, don't worry about associators. Suppose that I've got some composite in type theory where I forget all the unit data. So my composite is just wrong because the unit data don't match up. Can I put that back in? I get a much larger proof, but one that's actually correct, because that's morally what that would involve, right? Any Martin-Loeb type theory. Oh, thank you. It's actually my birthday today. My boys have just come back from school. I'm still still talking to my.
No, I think your boys just ended this talk, and it's a good time to end, maybe. We should let you go.